So hi again. So this morning and today, what we're going to do is a little bit more of the data analysis side of things. So what my thought is this morning is I'm going to give this talk on kind of introduction to data analysis. Most of the stuff in this talk are it's kind of intended of here's an overview of kind of what the community does and the different steps and the different options you have for physiology correction, motion, artifact correction, etc. So I'm going to go through, kind of explain some of that. It's a lot of, if you're reading through the literature, keywords that you tend to see in terms of, Rob Cooper's lab did principal component analysis, removing the first blah, 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 blah. What did that actually mean? So I'm going to go through some of that. Please ask questions. I know it's a little bit mathematically dense, but I try my best to explain it. After that, then we're going to switch over to, it was originally going to be advanced analysis, and what I decided to do was advanced had way too many equations. So we're just going to jump to how do you actually do this in practice, which I have a toolbox, and we're going to go through kind of a hands-on, walking through the data that we collected yesterday and talking about that within this toolbox for doing analysis. And then we can answer questions, and I can explain what it's actually doing. So this first talk, what we're going to do, first steps to data analysis, I'm going to walk you through the different steps of pre-processing, talk about some of the practical issues we have, mostly being physiological noise, systemic physiology, and motion artifacts, and then talk about some of the data analysis tools that are available out there for dealing with this kind of data. So obviously this is fNIRS. This is actually one of the really old Tekken systems, and hopefully you're all experts on that half of the slide now. And our typical data analysis, NIRX data comes here. You've collected raw data. It's been saved. Now what do you do with it, right? And so we're going to be talking about this whole pipeline of taking raw data, bringing it through what's called the Beer-Lambert law to estimate oxy and deoxyhemoglobin, then doing statistical testing, group level analysis, and eventually image reconstruction on that data. So I'm going to talk about the ins and outs of that. So the first step of fNIRS is conversion to hemoglobin. You measure raw signal intensity. It's the amount of light from a source reaching a detector. Anything that changed in the tissue in between that source detector obviously absorbs the light, and you get less light hitting that detector. And so that's the conversion of raw data to hemoglobin units is what's called the Beer-Lambert law. And it's a concept that's introduced in maybe freshman chemistry class in college, in analytic chemistry. But it's basically this idea, if I have a test tube and I shine light through the test tube, I can figure out how much, what the concentration is in here, as long as I know some of the physical properties, that is the extinction coefficient of whatever the compound is, and I know the distance, the path length that the light traveled through the tissue, or through the sample. And so in a chemistry class, this is really simple because you can take a ruler and go and measure that distance. It's 1 centimeter across the low cuvette or something. But it becomes a lot harder when we start talking about tissue, where the light going through the tissue doesn't go straight. It doesn't go ballistically through, it scatters. And so we know all about this here. But the light going through the tissue doesn't take a straight path. It wanders around, it diffuses. And so it might be, taking my finger as an example, it might be 1 centimeter across my finger, physically going straight, but it's probably close to 6 centimeters in terms of all the back and forth wandering that light has gone. And that factor of 6 is what's called the differential path length factor. It's a fudge factor, a scaling factor that accounts for the fact that light didn't go straight. And so what's called the modified Beer-Lambert law here takes in not the 1 centimeter path length, but this effective path length of the original distance times this what's called differential path length factor. There's an additional term, G, a geometry factor, that accounts for the fact that light can, because it's diffusing around, it can escape out the sides of my fingers as well as hitting the detector. and that's this geometry term. Let's see. And I will introduce, it's not on the slide, I'll introduce it here. One of the problems with brain imaging is there's actually two terms here that control the absolute amplitude of the NIRS signal. That is the micromolar, your estimate of micromolar units. There's this differential path length that the light just didn't go straight through. And we can model this using, if we have estimates of the structure, MRI, CT, something like that, we can model it with Monte Carlo methods or so on. We can model this diffusion and come up with that value of sixfold. There's also what's called the partial volume term, which is of this light going through the tissue, it went in through, the skin, skull, CSF, hit the brain, came back out through the skin, skull, or CSF, skull, and skin. And the problem is that of that 6 centimeters that it traveled through, only maybe half of, like 5 millimeters, was actually spent in the region that you actually cared about, the brain. So you have both this differential path length that the light traveled much farther than you thought it did, and this partial volume term of that full path length, only a small fraction of it was actually spent in the brain. And the problem is you need to know both of those terms in order to be quantitative. So typically in the NIRS community, we always talk about the modified Beer-Lambert law, and I think the NIRX software even has this term of DPF, and they put a value of 6. The problem is that doesn't account for this partial volume term. So when you're estimating 6 and you put 6 for DPF, you're actually overestimating the actual brain response. That's assuming that the entire path occurred, or the activity occurred in the entire path, which we know to be mostly skin and skull and so on. And so we have this additional term of partial volume. So typically our DPF, or what's called the PPF, the partial path length factor, which is a combination of both the differential path length and the partial volume, is typically something more on the order of like a half, meaning that of that 3 centimeter distance, differential path length is 6, but of that 18 centimeters, only half of that, only 9 centimeters was actually spent in the actual brain itself. And you have to know those terms to be quantitative. Fortunately, what I'll talk about a little bit later is if you're just worried about t-statistics, that term appears in both the numerator and the denominator and washes out, at least on a single subject level. Where you run into trouble is if you're trying to do group level analysis where you're looking at, say, younger versus older subjects. The older subjects have brain atrophy, the brain is moving away, which means that partial volume term is going to be smaller, which means you're going to underestimate the signal if you use the same term. So it's things that have to be considered. So anyway, I'll jump through this really quick because hopefully most people kind of know about this, the Beer-Lambert law. The idea by measuring 2 wavelengths, we have 2 unknowns, oxy and deoxyhemoglobin. We solve this 2x2 system of equations so we can estimate oxy and deoxy. And these differential path length terms or partial path length terms appear in this equation here that if we get these wrong, we're off by our amplitude estimates of oxy and deoxy end up wrong. Now, the choice of wavelengths that we use and why the NIRX systems use 780, 850, the Tekken systems use 690, 830. The reason why those specific wavelengths is because there's a bit of work, the paper by Gary Strangman et al. In 2002, I think, is kind of the one everyone points to, that basically showed that if you're selective in which wavelengths you use, although you don't know the differential path length, as long as it's the same for both wavelengths, at worst you're off by a scalar. Right? At worst your amplitude, you get oxy-deoxy relatively right, that is oxy is 3 times bigger than deoxy, you don't have crosstalk, but at worst you're off by an overall scalar factor of the entire system. If you choose the wrong wavelengths, what Gary Strangman showed was that it can actually lead to crosstalk. You don't separate oxy and deoxy correctly, and you end up kind of getting weird type responses and not the right shape, and then everything is wrong. So as long as you paid attention to which wavelengths you use, DPF for the most part is considered as a scalar factor that affects the overall amplitude but not the separation of oxy-deoxy. But it is definitely something to be aware of because every now and again you get a comment for a paper review or something dealing with crosstalk between oxy and deoxy that you have to address and then go point to this Gary Strangman paper. So anyway, so we've now collected our data. We've turned that oxy or that raw signal intensity to oxy and deoxy hemoglobins. We now have a time course, and the time course looks something like this. Hopefully, that you have your experimental design. This is kind of simulated data, but let's say a finger tapping experiment that you kept tapping your fingers, and you get this change in oxy and deoxy hemoglobin every time you tapped your fingers. So now what the goal, of course not all data looks as beautiful as this because you can obviously see it, do your stats by eye here. Now the goal is to do some sort of statistical analysis. I want to know what channels statistically changed during these task periods compared to these rest periods. And so by eye you can really clearly see it's these couple channels and those channels down there didn't change at all. And so if I map these on the head, and this was a finger tapping, the expectation would be these channels were over the motor cortex and these other channels were not. But as I said, most data doesn't look nearly this clean. And so that's what I'm going to spend kind of the rest of the talk talking about. So there's really two different schools of thought, let's call them, on the analysis here. And historically it kind of came from people coming into NIRS, where did their background come from? So in the NIRS community, historically we drew a lot of users, and I know this from this crowd here even, that you either came from having done previously fMRI experiments or EEG experiments. And EEG, the EEG people, which a lot of the the pediatric type imaging people that migrated into the NIRS field came from that EEG type world. The EEG analysis, we tended to favor deconvolution, block averaging type techniques, where you basically take every one of these blocks, you stack them up on top of each other, you average through, and you get something akin to an ERP. So we call that a HRF, a hemodynamic response function. But it's this nice curve that kind of comes up and so on. And so I'm going to refer to that as HRF analysis. Which is really where you're estimating the average response of the curve, and you're kind of looking at this at a time course. It's always a two-step process, because after you've now estimated this time course, you now have to do some sort of hypothesis testing. So you have to frame that as, well, I'm going to look at this window from, let's say, 6 to 12 seconds, and I'm going to compute the amplitude over that window and compare it to the amplitude of some other window, some baseline window. And so HRF analysis is always kind of a two-stage where you estimate the response and then you define a contrast window and you estimate the contrast over that window. The other school of thought, which are people that were much more familiar with fMRI and kind of came from that, was this idea of kind of jumping straight into the hypothesis by using a canonical or a parametric model. So people from the fMRI were familiar with AFNI or FSL or SPM, where the standard kind of in the fMRI community is you take your stimulus timing, you convolve that stimulus timing with an expectation of what the response should have looked like. So you've done 30 years of, the field has done 30 years of research, we kind of know that the hemodynamic shape should come up, peak around 8 seconds, come back down. So we're going to assume that our data looks like that, and we're going to basically ask which channels correlated with that expected signal. And so we're jumping in straight to the hypothesis of which channels were statistically, I guess it's the null hypothesis, which channels were statistically not related to that task or not related to that expected timing. So if the expected timing is wrong, I'm going to find, I might have a channel that was activated by some other definition, that had a slightly different timing, but I'm going to fail to find that because it didn't match my hypothesis. It's really just a case of I used the wrong hypothesis. But I'm going to refer to that as parametric modeling, and these kind of two schools of thought of estimating deconvolution or estimating the entire time course versus doing hypothesis testing. So let's see, I'm going to skip that slide, jump to here. So if you've done that experiment, hopefully, so this is the deconvolution version. So hopefully you would get some sort of response like this: the oxyhemoglobin goes up, volume or total hemoglobin goes up, deoxyhemoglobin goes down. This is really the result of the competition between a flow response in your brain and a metabolism, oxygen metabolism response. The flow response generally wins by 2 to 3-fold. We call that the hyperemic or positive fold response. And hopefully your data looks something like this, that these guys are going up and deoxy is going down. So if you followed that kind of deconvolution ERP, you've got something like this. You've got a time course, hopefully with some error bars on it. And what you would have to do then is you would pick a window of time. You know, in this case, this is a very short 2-second finger tapping data. So you might pick a window from, say, 5 to 10 seconds or so. And you would compute the average and the error bars for that window, and maybe you compare it to the average and error bars for some baseline window. People also do, although I don't advocate it, looking at peak amplitude or time to onset as a statistical parameter. But somehow you take this hemodynamic response, you compress it into a single test. Is this window different than that window? And that's what you do your stats on. Considerations for that are what window to use, because obviously if one of the problems with this kind of analysis is you're tempted to change your hypothesis after you see your data, right? I mean, if I looked at this data and I said, oh, 5 to 10 seconds, I said 5 to 10 seconds because that's what the data said, right? If I was up here and the data was shifted, I would have said a different window, which means that my hypothesis is going to favor kind of false positives, right? Because I'm always kind of tempted to lead my hypothesis to match my data. So that's definitely an issue. You also have this issue of multiple comparisons, because in NIRS, and I'll talk about this a little bit more, we have what's called serial correlations in our noise. Our noise is not white. It's not instrument noise. It's what's called color. It has specific frequency components to it. Cardiac, respiratory, blood pressure are slow physiological changes that are much slower than our data rates. And so a lot of this noise is due to that, and which means that the error bars at this point are not independent of the error bars at this point, because you had this slow noise that was moving through the data. And so taking a window of time, you might have, let's say, 100 time points within this window, but you don't actually have 100 degrees of freedom. And so you have to somehow correct for that in order to get your statistics right, because you're actually underestimating the noise, or overestimating the degrees of freedom when you do that problem. So actually, I don't have this slide I was looking for, but I'll go to this. So kind of the HRF analysis, you get to see more of the data. It's more of an exploratory, but you have this maybe user bias that unless you predefine your windows, you might be tempted to change your hypothesis. It's more flexibility in that sense to test different things, like is the timing different between my two populations or whatever. The other problem with HRF analysis is you can only average things with the same duration, right? So if you tap your fingers and you do it for 10 seconds and you repeat that in every single block you did it for 10 seconds, you're fine. But if you're, and a lot of the psychologists I work with, they do some sort of cognitive testing with E' that requires a response from the subject, which means that each trial can be a different length. because in some trials the subject didn't respond as fast as the other trials or whatever. And the problem is if that's the case now, if I stack all the data and try to average through, all of that jitter in the timing, the response timing causes problems when I do the stats, right? That I have to somehow correct for that. If you're doing kind of more of the parametric analysis, which is the fMRI style, as I said, what you do is you take your timing, you convolve it with an expected response, you deconvolve, and you just test, did that response correlate with your data? Well, if you do that, now you have more flexibility, because if you have that information that this trial was longer than that trial, that actually gets incorporated into your hypothesis, into your expectation. So these kind of SPM analysis can deal with variability in response timing and so on. You had a question? Or, yeah. Well, it's if you do the experiment wrong. Of course, if you brought it to your statistician, they would have, the first thing that they would have asked you when you entered their office was, what time window do you want to use? Yeah.
So there are a couple of different strategies, right? So presumably you have some set of contrasts that you're interested in. And I understand completely that you might want to go in and say, I'm going to define my time window up front.
Yeah.
But the question is this. So let's say you're working with a population where that HRF is not well defined. Would you see it as sort of still high probability, bias to the data if you took independent of condition the population that you're working with and just look to see where that peak in that HRF was, but independent of condition and consistent, let's say, baseline?
Yeah.
Would that still be biased?
Well, no. If that was the case, your hypothesis is, did this population differ from that one, or did this condition differ from that one? And that test, by choosing the window, as long as you were consistent between the two, then you're fine. You don't have that bias. It's really if you're testing it against, did this condition activate relative to a baseline? That's where you run into the bias, right? Or you looked at the two conditions separately and said, I'm going to use this window and I'm going to use that window. That's a problem, right? But yeah, you can get around it doing like that, but you have to be conscious of what you're, of those type of questions. And I don't want to knock the NIRS field at all, but historically we haven't been the greatest group when it comes to some of those questions and some of those hypothesis testing. Okay. The more recent stuff, and I might throw up a slide later on that shows this, but I'll jump to some of the new stuff that we're doing. That it turns out, and I'll show this a little bit in the toolbox. So I said this way, it's a two-step model. You estimate the hemodynamic response, and then you choose a window and estimate over a window. Whereas this, you jump straight to a hypothesis. If you chose the window correctly, if you chose the window of well, actually, I know that kind of comes up, peaks at 8 seconds, comes back down, and instead of using a constant window of, I'm going to give equal weight to all these time points, you actually give a tapered window that goes up and comes back down and use that as your contrast, you get the exact same answer between these two methods. So you can do a full deconvolution, look at the whole time course, and then choose a tapered window that had that shape of the canonical response, and you would have gotten the exact same t-value as if you did it over here. The advantage over here is you're jumping straight to that answer, so there is a little bit more advantage in power. Weighting it by time. So if you use a tapered, this method, so in the NIRS field, and I'm glad you asked that question because it's exactly something that the NIRS field has criticized the fMRI people about. Of, hey, I do kids. I don't know what the hemodynamic response looks like. I don't want to make assumptions like that. It turns out that the canonical model, the way to think about a canonical model is not imposing a specific shape. It's imposing a hypothesis. It's imposing the shape of, what time window you want to use, such that if you use the wrong time window or use the wrong shape, it's equivalent to just picking the wrong time window. And so it's not. It turns out not. image babies, I don't know what the shape is. It turns out that that really wasn't as big of a deal as we thought it was. I have a new paper that's about to come out that looks at, it does nonlinear regression and estimates the response and actually looks at some of these issues of, does simulations of, puts in data with a kind of a wonky hemodynamic response that peaks much later than my canonical and asks, well, how bad is it, right? I used the wrong model, how bad is it? And it looks at this as a function of the duration of the task. And what it turns out is that if your task is longer than about 10 seconds, it doesn't matter anymore. Because the shape of the hemodynamic response, this wherever I had the last couple slides where it goes up and peaks, if I shift the response or I have a slightly different response, it affects the transients, that is the very early seconds and the very late seconds. But if your task is long enough that it kind of goes up and stays up and then comes back down, if the task is long enough, it no longer really matters. And so if you do sensitivity specificity analysis, using the wrong shapes and stuff, you find out that it really doesn't matter all too much if your task is longer than about 10 seconds long. If your task is shorter than that, then it becomes really important to get the right shape. And if you have the wrong shape, you have type 2 error. That is, activity is actually there, but you fail to report it, so you have a false negative. But we're going to publish something that's going to come out that says above 10 seconds, which is the vast majority of 10-second duration of the task. It's true for both event-related and block design. There's a little bit, when you go to event-related, there's a little bit of a caveat with what I said about choosing the window right, but but yeah. So what I'm going to show it in my toolbox in the second talk. My lab almost exclusively does this version because there's a huge statistical power associated with this version, and almost all of our experiments are dealing with tasks that are longer than 10 seconds long. And so we always do this. But I'm going to show you both ways within the toolbox and leave it to you to decide which one you like better. So I kind of got sidetracked a little bit on that. So I'm going to jump in some of the practical issues and how historically the field has dealt with them, and as I said, kind of give some background in this. And I'm actually starting to run. I have till 11, right? Ish.
So 12:30 is when everything's done.
Okay, so let's go a little bit faster. Okay, so I showed some data before that was nice, clean. You clearly saw the responses, but most of the time your data looks a little bit something more like this. That we clearly have a motion artifact in the data. Motion artifact for fNIRS is when the probe moves relative to the head. So I can move around all you want. I showed yesterday all my work with gait, mobility, and stuff like that. Probe remains fixed. As long as it remains fixed, I can dance, I can do Nintendo, whatever. But as soon as that probe starts sliding on the head, the light that's going through the tissue is orders of magnitude weaker than the light that's just bouncing off the surface. And so if it lifts off even transiently, you're going to flood the detectors with an order of magnitude change in light. And that's why you get these huge spikes like this. So you get two kinds of artifacts generally with motion. You get what we call a spike artifact, where it comes up and comes back down, or you can have a shift artifact where it comes up, comes back down, and goes to a slightly different spot. So you actually see the beam intensity change before and after the artifact. But those are kind of the two types of artifacts that you deal with. If we zoom in here, we also have, so you see cardiac oscillations once every 60 beats per minute or so. You see respiratory oscillations, so generally people breathe at about 1/4 of a hertz. So you have an oscillation every 4 seconds or so, which is the breathing rate. Typically, you see the cardiac oscillations on the oxyhemoglobin channel, because that's more of an arterial. You typically see respiratory on a little bit of both the oxy and the deoxy. Here we're looking at oxy. And then you see, blood pressure oscillations, which are more variable and much slower. But you have these kind of waves. Thomas mentioned yesterday the so-called Mayer waves at 1/10 of a hertz, or slower drifts over minutes to hours to days due to blood pressure type changes. And so you have these very slow oscillations. Blood pressure tends to, as I said, cardiac tends to show up a little bit more on the oxyhemoglobin. Blood pressure and respiratory tend to show up a little bit more on the deoxyhemoglobin. So you have these different frequency bands to deal with the fast cardiac versus the slow blood pressure type oscillations. And then our hemodynamic response is typically kind of right in between, which causes a little bit of issues with filtering that I'll explain in a second. But it's slower than the heart rate, but probably faster than the blood pressure oscillations. And one thing I'll just show is these oscillations. Does this movie play? No, it's not going to play. That's right. This was a paper from Mariangela Franceschini from MGH. But what we did was we did a whole head imaging and mapped out these different physiological components. This was supposed to be a movie, but what you end up seeing is if you look at the cardiac, the whole head is kind of moving in unison because it's you know, your heart rate's pumping. But if you look at more of these slow drifts like blood pressure, what you see is the blood pressure actually starts in the back of the head where your venous sinuses are, and kind of you've got a rolling wave that kind of moves from back to front as this pressure wave moves through the system. So you have these very unique temporal and spatial features of the different physiology. This is just an example. This is Teresa Wilcox's lab. Is something I talked about yesterday. The little babies watching the puppet show that during the rest period, this is actually off the chart high. You get these huge motion artifacts, so the baby's moving around. During the task, beautiful hemodynamic responses, but during the rest period, craziness. And so if we take those ideas of the statistics, and I want to estimate the average amplitude here and compare it to the average amplitude here, well, the averages are different. The problem is the error bars on this part, the baseline period, are so large that I fail pretty much every statistical test I can do, right? And so that becomes a problem with this. And we talked about it a bit yesterday with that. So there are options historically for dealing with these types of artifacts. And so I'm going to walk through some of those different options. And they basically either make use of spatial features of the data or temporal features of the data. So I'm going to go through these. I'm going to start with the temporal features one. So the easiest one, and something that's was in the software for real time that Thomas showed yesterday, or in our homework code and so on, is a bandpass filter. So for something like cardiac oscillations, fast oscillations, Thomas showed yesterday, if I put a high pass filter, a low pass filter. A low pass filter is going to allow frequencies lower than the cutoff to pass, low pass. And so if I choose a low pass filter at, say, 0.5 hertz, all that cardiac oscillations at 1 hertz, at 1 beat per second, is going to get filtered away. And so you see if you apply a low pass filter at the right frequency, you can remove all this cardiac but leave presumably what is the signal of interest. The problem is if you choose the low pass much lower, so now we lower that threshold, now we start to wipe out a signal that potentially was of interest. And so one of the problems with a high pass filter is the opposite. A high pass filter lets high frequencies pass, and so it removes slow drift but lets all these high frequencies. And so a bandpass filter is you take a window, you cut off anything below or anything above that window. And the problem with bandpass filtering is selecting the window. Cardiac, easy. 1 hertz, you know you can remove it safely without really affecting your hemodynamic response. Blood pressure, respiratory, because the frequencies overlap with the frequencies of my hemodynamic response, it's a lot more troublesome. I have a hard time designing a filter that's going to safely remove all of that physiology and leave and have confidence that I'm leaving the signal I care about untouched. But people still, to this day, kind of use bandpass filtering. I guess this is the slide I was looking for. of I'm interested in this, so I could high pass filter away the instrument noise of cardiac. I could probably low pass filter or high pass filter the really, really slow blood pressure, but I have trouble kind of in the middle. And here's just an example: low pass filter, high pass filter, over filter, and I wipe the response. You get the idea. So that's how people used to do it, and there are a little bit more fancy ways in the literature to try to deal with that. One of the ways people have proposed is by using kind of essentially adaptive filter or wavelet filters, where it's not a specific frequency cutoff so much anymore, but kind of trying to remove some sort of trend. You still have the concept of overfitting, where if you choose the parameters too high, it removes too much of the signal versus getting it just right. This is the methods that are currently used in fNIRS SPM. So the fNIRS extension to SPM, it's what's called a minimum descriptive length wavelet, where what they try to do is they use a wavelet, so like a frequency type filter, and they try to use the lowest order wavelet that cleans up the data. So they're trying to avoid they're trying to avoid overfitting and removing too much. And so they kind of have a criterion for trying to remove the optimal amount of noise, leaving the signal untouched. I won't go through the math on that. Another way that we talked about yesterday a little bit. Actually, what is? Oh, this is not the slide yet. Forget that sentence. Actually, I'm going to skip that. I'm going to come back to that one because that's jumping. Another way that people try to remove physiology. That was a motion correction slide. I'm going to finish the physiology and then come back to motion. Another way people try to deal with the physiology is to externally record it. So say I have a subject, I can put a pulse oximeter, I can put a respiratory belt, I can maybe even put a non-invasive blood pressure, a beat-to-beat blood pressure on there, and I can remeasure some of this physiology. And so the idea is that knowing that external physiology, I can then design a filter to remove it from the brain. And so this is actually fairly popular in fMRI, where we record physiology and we use methods, what's called retro-ICOR, and so on, to put in these external variables as filters to clean up the data. We can do the same thing with fNIRS. And the idea is I measure all these things, or I measure everything I can off the body, and then I design some sort of filter that's going to remove it from the brain. The problem is, so what you do is you put them in as some sort of regressor. You have to actually estimate what's that transfer function. That is the excuse me, the cardiac signal, the heartbeat measured at my finger is not the same as a heartbeat measured at my brain. At minimum, there's a time lag between the two. And so what you have to do is you have to put in and try to model that time lag. So you put in lags of the heartbeat signal at the finger and try to estimate that as a filter. This is just an example. This is simulated data. This was actually from the original Homer. So if you download Homer, I think this is one of the data sets that's in it. But you have data here that's heavily corrupted by cardiac and respiratory and stuff. You have these different blocks which are an event. If you just average through, you get something that's really, really, really noisy, right? And that's because you don't have enough blocks to get rid of this cardiac or get rid of these noise oscillations. If you had enough trials, eventually it would go away because it would average to zero. But for a limited number of trials, which is the entirety of all the work we do, is always a limited number of trials. It doesn't go away yet. And so if you go and you measure that and you put in now two regressors, one that's trying to model that cardiac oscillation and the second one of interest that's trying to model the hemodynamic response, you can now remove that signal and clean it up. So you're modeling that original data as a linear combination of the response you care about and nuisance responses that you don't care about that are modeling these types of noise structures. I'm going to skip that one because it's, yeah. Mm-hmm. Mm-hmm. Yeah, that becomes a problem, right? So if you're if yeah, the major problem with all of these methods are that they assume, call it, independence between your task and your physiology. I said yesterday that if I even do a finger tapping task or certainly running on a treadmill, my heart rate went up correlated with the task. And so separating out based solely on the time course, what is a cardiac, what is the systemic versus the brain signal is going to be very difficult. Ask the question again after we go through the spatial methods, because in that case, the spatial methods are going to be what helps you, okay? And for the sake of time, I'm going to jump through a little bit of this quickly. People do adaptive filtering. So we've done a number of adaptive filtering methods that try to. One of the problems with this kind of method is it assumes that lag from my finger to my brain is constant, right? And if I'm sitting still, that's probably true. But if I'm running around and I'm jogging or something like that, every time my hand goes up, the transfer function is going to change. So if you have, so this assumes a stationary a stationary relationship between what I measure at the finger or the heart or whatever and what I measure at my brain. And if you're changing your posture, whatever, that's going to change as a function of time. So the way that people get around that is to try to do adaptive models where they allow those transfer functions, those relationships to evolve over time. You put some sort of restriction that they evolve slowly. They don't. So you're kind of, think of it like a sliding window over your data. But there's been a couple of groups. We use this for real-time imaging, where we have both adaptive filters that model out the physiology and then adaptive filters that model the brain activity, such that we're getting a updated model of brain activity. In this case, this was a finger tapping experiment, and we were able to show our model was able to switch. Our model only knew when the task occurred. It didn't know if it was left or right hand, and was able to switch back and forth between the two state conditions, left and right, with this. Yeah, I don't want to go too much into the math. Gets a little complicated on some of this. I just want to throw out some of the ideas, because when you read through the literature and you look at some of the reviews, they do talk about adaptive filtering and regression and these kind of methods, and you should at least know what the terms sort of mean, or at least what they're referring to. But as I said, those are all temporal methods. They're using this idea that I can identify cardiac because it's fast, or of that nature. Spatial methods try to take advantage of the spatial structure. The fact that I said if you look at the cardiac, it's actually the whole head kind of going like this. And so it has a lot more spatial structure. It's going to be all over the whole probe, whereas brain activity might only be a very focal, local, regional activity. And so we can kind of use that as a filter to try and move things that are global from the signal versus brain activity that's very local. Actually, this is kind of, I'm going to come back to that one too, because that's kind of a hybrid between the two. Anyway, so this is again that same image from the whole head Mariangela paper, where she looked at the spatial structure of heartbeat, respiratory, and blood pressure. I'm sorry, this also was a movie that was supposed to animate, but this is, the heartbeat is going like this, whereas respiratory and blood pressure are starting in the back of the head and kind of rolling forward as a time course. And so what you can do, oops, what am I doing? So one of the ways that we can do this is what's called principal component analysis. So principal component analysis. This is a terrible. Okay. So principal component analysis is a mathematical technique for decomposing a data matrix into, for lack of a better term, its principal components, the features that describe the most of the data. So the first component, the strongest component, describes the strongest feature in the data. The next component is the next strongest out to the last component, which describes the fine details. And so what you can do in principal component analysis is kind of likened it to frequency filtering, that we can take our data and decompose it to different frequencies. We can then remove certain frequencies and rotate back, and so we now have the data in the original space minus the cardiac frequency or whatever. That was what we talked about for the bandpass filtering. PCA, very similar kind of concept. What we do, so with the frequency, we decompose in frequency, cut out some of the frequencies and rotate back. With principal component, it's the same sort of concept, and I'm sorry my equations are failing a little bit. But we can take our data, we can decompose it into this principal component space. We can identify which of those principal components look like cardiac or look like respiratory. We remove them, we zero them out, and then when we rotate back to the original space, now that feature has been removed from the data. Okay? So people actually, this crowd, it seemed like a lot of people did EEG, PCA or ICA, which is a very similar type of method, unless you're a mathematician, then you'll crucify me for saying that statement, are widely used in EEG for things like heartbeat removal and eye blink and stuff like that. Same concept in NIRS. What we do is, yeah, I'm trying to think how I want to describe this. I don't want to go through the math of what PCA actually is. But what we do in NIRS is we take the spatial covariance, so channel by channel noise structure, right? So things like the cardiac oscillation are going to be very global features. That matrix is going to be very full because all the channels were moving together, okay? Other features like finger tapping or whatever are going to be much less dominant features. They only affected a smaller number of channels, okay? And so what we can do is we can take that covariance matrix, we can do a principal component analysis, and we can remove the first couple of components, which are the features that were spatially global. So if I go and I take my data and decompose it, I know that first component is being the strongest global feature. And if I remove it then and rotate back, what I'm going to be left with is a much more focal, things that affected only a focal area of activity, okay? If I go the opposite and I remove the last couple components, those are things that only affected like one channel. And I know brain activity is probably a cluster of channels, depending on my probe design, but it's probably not all the channels. And so you can use this kind of spatial feature to filter out your data. Yeah?
So that, by that logic, this is less of an effective strategy if you do expect that
Yes.
your channels to be doing something similar, but what you're doing is you're
So PCA, when we jump to my toolbox, the next lecture, I'm going to kind of undo everything I'm saying here because we don't do any of this stuff now. We found better ways to do it. But but because that's one of the problems with PCA. The other problem is it works really well if your probe is large. In this case, my probe is the entire head. Cardiac is moving the entire probe, and I have a lot of channels where I didn't expect any brain activity. And I'm using the fact that it showed up in those channels as to know it probably wasn't brain activity. But if you had a very small probe, maybe you do children, where you don't want to use 32 source detectors, you only want 4 across the floor, a very small probe, brain activity could be 50% of your channels, right? In which case, it's much, much harder to separate it out from a global signal versus a more regional signal. Okay, so this kind of PCA really only works if your probe is large enough that you have a lot of areas where you didn't see brain activity and you didn't expect to see brain activity. Okay, but if you do that, this you have a probe like this. This is from Mariangela's paper again. This was a finger tapping or a median nerve somatosensory, but you expected activity here if you just looked at the signal with no pre-processing. You end up getting a very global response because every time I tap my fingers, it turns out my heart rate went up, and so I have this very global signal. If you do the principal component and you remove the global components, the global signals, you're left with this just the motor cortex, so the sensory. I don't remember if it's a median nerve or a motor task, but you're left with activity just right there. The problem with principal component analysis is, one, I said you have to have the right probe, it has to be big enough, and two, how many components to remove and which components becomes a challenge. Just like filtering, if I remove too many components, maybe the first component, okay, knocked it down, maybe the second component, it's more focal, remove the third component, all of a sudden what I was calling brain activity disappeared because I've over-filtered now. There is a question of where do you stop and how did you know to stop there? And I would argue that the statement, and this is knocking my own work, the statement of I removed two components because what was left was the motor cortex probably isn't a good answer, because it's you remove the number of components until you saw what you wanted to see is probably not the best way to do science. So one of the problems with PCA or ICA becomes how do you identify which components to remove and how many. And so people we recognize this. Mariangela is a good scientist. She always has some version of an objective criterion, such as I'm going to remove the number of components modeling up to 80% of the spatial covariance. So she has kind of a criterion that she starts with, and she does it that way. She doesn't just look at the data and stop when she sees a good response. But not everyone follows that practice. And I'm sorry if I'm making fun of people. This is just another example. This is my student Ben playing Dance Dance Revolution, which is kind of a reaction time sort of task with your feet. But if you do that, had a before image that you have this huge kind of global response, maybe you could say there was a little bit of activity there. But if you do the PCA, you get a much more focal. But again, how did I know that that was the correct response? I don't have a good answer for that one, other than that's where I expected it to be. PCA can be used for both physiology or motion correction. And same thing is true for motion artifacts. Motion artifacts, depending on the size of your probe and the configuration, tends to move the entire probe. The entire probe lifts off. And so that's less true if you have multiple patches of a probe or over different areas which are going to move a little bit more independent. But we've used PCA in the past for motion correction, the same idea that the whole probe, all my channels are moving. When we do PCA for physiology, what we typically do is we calculate it separately for oxy and deoxyhemoglobin, because we know the spatial pattern, oxyhemoglobin has more cardiac, deoxyhemoglobin has more blood pressure, and they're going to have slightly different spatial patterns. So we compute it separately for the different wavelengths or the different types of data. With motion artifacts, there's no reason to believe that the probe lifted off the head and only affected oxyhemoglobin and didn't affect deoxy. It doesn't care. It's just the whole probe, all the signals across all your wavelengths change the same way. And so when we do PCA for motion artifacts, we actually put in the entire matrix, because now we're looking for features that didn't care about wavelength. And so that tends to be a lot better for motion artifacts, because again, motion artifacts don't care about wavelength. They affected the entire data. And so this is an example. This is Teresa Wilcox's data again. And I said huge motion artifacts during the baseline period. If you remove the first component, you knock it down. You remove the first and second spatial components, you get knock down this noise, but this part remained mostly unchanged. If you started filtering more, this would start to disappear. So again, kind of where do you stop on things? I'm going to jump back for a second on this one of the slides I skipped then. Because those were all methods that people used in the past. If you've used my software, Homer or Homer 2, all those methods are in Homer and Homer 2, and that's the way that we used to do it. And it's really nice in some cases. The problem is, a lot of people, we build the tools and it's like, hey, it works in this data set, and then because this data set has a large probe or certain types of noise structure, and then you'd move to a different data set and the tool would no longer work as well, or we'd have to write a new tool and so on. So there was no one-size-fits-all type approach, and we were posed with all these different questions of how many components to remove and so on. So those methods are still out there. They're still, I would say, actually the majority of fNIRS research still use those tools and those methods, which is why it's important to be aware of them. There are options, and I'm not going to, if I'm the reviewer on your paper, I'm not going to fault you for using those tools as long as you're aware of the limitations and so on, and kind of think about some of the issues I brought up here. Where the field is going a little bit more recently is, and something Thomas mentioned, is the idea of short distance measures. And short distance measures, what you do is you have a source detector at different spacing. You have a short one at maybe 1 centimeter or shorter, and then you have a long one. And the short one, because the light doesn't diffuse into the tissue as deeply, is only really measuring the superficial. The long one is measuring both superficial and deeper. And so what you can do is you can use that short distance as a local estimate of this noise structure, and you can design your filter based on that, and then apply your filter to remove that same noise structure from the farther distance. And so, like Joe Culver's group at WashU and Rob Cooper's group out of UC London have been huge advocates of this type of approach. The downside is you need specialized fiber optics or instrumentation to be able to measure that. You need at least, you need fiber optics with multiple distances, as Thomas showed. You need an instrument that has enough dynamic range, because the light at 1 centimeter is an order of magnitude or 2 brighter than the light at 3 centimeters. So you have to be able to model that dynamic range. It does depend on wavelengths. I think with the NIRX systems, it's less of an issue because your wavelengths are higher, but with my system at 690 and 830 for the wavelengths, the 690 wavelength dies a lot faster as a function of distance. So they might be evenly matched here, but down here the 690 is about 3-fold brighter than the 830. So it's almost impossible to match at both. You match the intensities at both distances, and that causes an issue with my systems. But what you do that measurement, you use the short distance as some version of the regressor, and to remove it from the large distance. And there's a number of different ways to do it. Rob Cooper, Joe Culver here, they're using it as a time series regressor. So you use the time series of the short distance and you remove it from the long distance. So very similar to what I described, the external measurements, pulse oximetry and stuff. There's other people, and the method I use for this is I actually do a PCA of just the short distances, and then kind of a little bit more complicated than that, but I do a spatial map, a PCA of the short distances, and then remove that from the long distances. A little bit more complicated than that, but that's the general idea of taking both the space and time information and so on. And I think you're going to see a lot more of this in the literature. There's some circles of fNIRS, like the ones I have to publish in, which are most being reviewed by people that do only methods, where they almost insist that you do this kind of stuff. I think it's a great idea to do short distance measurements. I feel that the field has not yet defined what the best approach to it is, but we all recognize that it should be done. So, yeah.
there are two there's two questions kind of embedded in that. There's what does it mean to be short, and how many do you need? So Rob Cooper's group out of UC London published a paper recently that looked at distance. So he looked at different distances and how deep does that actually go in the head in both infants and adults. Because if you make it too long, you're actually getting a little bit of the brain you can end up overcorrecting. So you have to read the paper, just don't quote me on the numbers, but I think in adults it was on the order of maybe 13 millimeters or so was what they considered a good optimal short distance. In infants, it was an almost unrealistic 3 or 5 millimeter, which means you have to get, do you remember the
Actually,
numbers?
yes, it's even less. So it is spatially dependent as well. So in the forehead, for adults, it even gets as close as I think it's 8 millimeters.
Okay.
So it's pretty close for forehead measurements. On infants, it's like a couple millimeters. To the point where that's closer than the diameter of both tips.
Yeah, you just can't do it anymore.
Yeah.
And then that's the other half of the question, because there's, I think Rob's group is more in favor of you just have a couple around the head. Rickson Mosquito, who's out of Brazil, he came from the UPenn group, he is adamant that you actually need one, not for every source detector, but a short distance for every source and a short distance for every detector. That for every one measurement that you care about, you actually need two distances, or two, on both sides. So I think that's a little overkill. I think the problem with that, while from a physics point of view, maybe that is the best solution, I think from a practical point of view, I'm not willing to sacrifice 2/3 of my detectors to do that measurement. Because now I'm going from an 8-channel NIRX system to a 24-channel NIRX system just to do that. Unfortunately, we don't have a great answer for it yet. I mean, you're probably asking, what kind of system should I buy, and how many detectors am I going to need, and do I have to worry about this?
I can show you what we have. We do have the way things, basically it's specialized. That I have here. But for the time being now, I think we'll keep going. And it is 11:20.
Okay, so we'll stop and switch if we want to take a break, and let's switch over to the other stuff.
It's your time, so
yeah. Let's do that. Let's stop, take a little breather, and then we'll come back and deal with toolbox stuff. Yeah. You don't want to do. Yeah, if you just take the global average and use it as a regressor,
It seems like it was all there's concerns about the exercise research, like are we just measuring skin blood flow, or are we just measuring
Yeah, with movement-related fNIRS, it's particularly difficult and an issue.
yeah, what you actually want to do, I don't think it works. I mean,
Yeah, it is fair, and it is particularly difficult. So before I even get into this too much,
one thing
like I said, we don't recommend spring-loaded. So this is a spring-loaded solution right now. However, you could use it with. You shouldn't use spring-loaded with motion. However, you could use these with our fiber optic TMS programs. So we would need to come with something that is basically more like the standard ones, like these ones.
That works a lot better than
like this, but not so hold it tighter, but not spring. What we have is spring-loaded. These are actually fibers. These tiny little fibers, and that's exactly 8 millimeters. That's why we have it at that distance. So that way we know we're not going any deeper than we should. I mean, there's an ideal distance to get like right in the middle of the skin in that area. But if you're shallower, that's not such a problem, right? As long as it's at least several millimeters you're getting in there. And so yeah, this is just the ring itself for the sphenoidrometer. And yeah, tiny little fibers here and here. And it's actually only something that's particularly innovative that we did is all of these are connected to a single detector because we multiplex. You're only sacrificing one detector, then to get 8 different short channels. So you don't have to have 8 different detectors to get 8 short channels. And that also is an issue and was important because your system actually can saturate. So we had to split it up because otherwise it would saturate. Like if we try to do a single detector measurement that's this close with the source of detector pairings with the fNIRS board, you would just have saturated signal. That's a problem. This has a much larger, I should say, lower dynamic range. The sensitivity is at the same level at the high end, but when you get down, this one will not saturate. That one will. So you take this and actually like that. So I plug one of these detectors into this connection. These guys are making their own systems, so I'm being a little careful about what I show because
I mean, ice works a lot better.
we're not in the business of showing, especially prototype things. Exactly. No, I know, and you're already a customer. So it's a little.
But in reality,
you can see the light changing in those tiny little probes. The other two are just mechanical, just to keep it stable. So we would need to prototype something for the other sport, for the other grommets, really, not surface sport. Because actually, I'm personally recommending. The other thing that reduces the signal is this is a super inefficient way to couple, but that's a good thing. You don't want too much signal. So normally you would never do this and expect that you get good signal. It's really, you're losing at least half the signal just doing that, but it's not a big deal because it's so close. You don't have a but coming back to it, with child applications, and that's where I think we can especially justify and push a lot more because
it's something very similar.
it's not that we don't want to work with labs. You know, I said yesterday, it's not as much of a focus for us. The problem that we've had is we've had so many people purchase a news report for studies that are not cited, and approaching it in a quantitative way, and not really.
yeah, exactly. They don't present in our conference.
Just the support is so difficult already. But you're doing it in. You guys are really doing it in a way that is the right way. You want to isolate. A lot of people will say like, "Hey, let's just walk around outside and do all kinds of things." And what kind of questions can you ask them? There's too many variables to try to isolate. So we need to look at prototyping some things. That's about it. I mean, that's all I can say with that. I don't know. I guess the other thing we could do is have a top that is still wouldn't be quite as sturdy. It still wiggles just a tiny bit. The other one's still better. Even if this was firmly in there or at some distance firm, it still would not be as good as the other grommet. I'm just thinking out loud here mechanically. So we need a grommet that would fit with this other one. This is like the style you have. And we could flip it over, and that would work in that sense, and it would kind of fit around it, but we just need something Let me write this down.
A lot of studies that are done and exercise.
Oh, it doesn't correlate with
exercise.
there's a bunch of papers titled things like dozen years ago.
Right, and you'll still have obviously the other issues to handle, like you were saying, with blood pressure and heart rate and everything, but at least you know that it's
But they look at for some discipline. I was surprised.
That's definitely especially considering it's not just movement studies and exercise studies, which is important to us still. It's just any child or baby study, you're going to have something similar. You have to have the ability to deal with emotion in the same way. They just don't. They're not going to sit still. Even if the experiment is sit still, they're not going to sit still. They're just not. Not until age, at least consistently, not until like age 7, 8 or so, are you going to be able to get a significant majority of the subjects behaving for a good amount of time. Like Tito says, she designs 4-minute experiments. 4 minutes, that's it. She said 4 minutes, it is a long time. She said that's the maximum. Like to get in there, do an experiment, and then you have to be done. Because after that, you might not be measuring anything to do with what you think you want. It's, the attention span is very short. So we gotta work on something. Well, the thing is this. So the hardware is done for this next generation imager. And software is not. So a huge amount of the computer resources are dedicated to use for tools. I mean, hardware developers are separate, so there are aspects of it that we're like changing some add-ons and things. But I have a question actually for you related to this. Do you do any accelerometer measurements? So the group at Stanford, Alan Reese's team, they've got a bunch of systems from us, and they were using Project before. They've now worked with a bunch of different labs in California. They make their own accelerometers using, I think, an Arduino, might be Raspberry Pi. Those are basically inexpensive. It's like the systems they built here based on that. You buy a little printed circuit board that's made for this, and so that's what they do. They made their own accelerometers and they just put that on the tab. And that will be something in the next generation one that's already built into it. But that's to know like the head motion and quantify it. But for the time being, it's not that difficult to do something like that. Getting in touch with them to see like what kind of code do you have, what were the. They're super nice people. I'm sure they tell you like what is it you have, and you have code you be willing to share. Because it's not like we're not doing anything similar to what you guys are doing.
So we can kind of
So I don't think they're such nice people. It's a huge multi-study center, so I'm sure they'd be happy to
It's in there. It's coded in there. It's not pull it up on the data.
No, it just is another related. That's more like when is it a particular problem? But
I just want to see
yeah,
what is happening.
temperature changes.
I'm not doing any more.
That would be there as well. That I wanted to ask you. Measure that. That might be. Well, that's the other thing that with the Arduino that I was going to suggest that I haven't had a group that I came up with until I was talking about it. Is did it Raspberry Pi or Arduino? I don't know which one it is. It doesn't make any difference. But either way, you can attach sensors. You could then have on the inside of the cap like four heads, like a little surface temperature to know, okay, what's the temperature of the subject's skin, to know over time how's that changing. And that can be pretty important because that will then also be, especially a slow change, very kind of effective. With LEDs, it's less of a problem. Lasers, temperatures can be a pretty big issue. But
Very close to Halloween.
yeah, there are a lot of things to do.
Yeah.